Welcome, dear students, 2021 Unit 5 Mechanics paper CC-10 Semester 4 Mathematics Honors, University of Calcutta. Question paper 2021 Mechanics paper Unit 5. Unit 5, question paper Unit 5, question 7a 1. Define linear momentum of a multiparticle system so that in any motion of a multiparticle system, the rate of increase of its linear momentum is equal to the total external forces acting on it. Linear momentum of a multiparticle system. If a particle has mass m and velocity v vector, then its linear momentum is given by p vector equal to mv vector. This is for the single particle. Let S be a multiparticle system consisting of n particles p1, p2, pn with masses m1, m2, mn and velocities v1 vector, v2 vector, vn vector respectively. The linear momentum p vector of the system S is given by p vector equal to summation over I equal to 1 to n mi vi vector. And second part of this question, then so that in any motion of a multiparticle system, the rate of increase of its linear momentum is equal to the total external force acting on it. Actually, this is the linear momentum principle. For a multiparticle system S, the rate of increase of its linear momentum is equal to the total external force acting upon it. That is ddt of p vector equal to F vector, where F vector is the total external force acting on the system S and P vector is the linear momentum of the system S. A proof, let S be a system of n particles P1, P2, Pn and is acted upon by external forces F1, F2 vector, Fn vector and internal forces Gij vector as shown in the figure. So this is the particle Pi and this is the particle Pj, and the external force on Pj, this Fj vector, and this external force on Pi, Fi vector, and this on Pi, on the particle Pi, the internal force, this Gij, on the force, internal force due to particle Pj, on this. And similarly, Gji is the internal force on the particle Pj due to particle Pi. The equation of motion of the particle Pi is given by mi, the mass of the particle at the point Pi, and ddt of vi, velocity of the particle Pi, equal to the external force Fi. Actually, this Fi is the external force on Pi, plus summation of all internal forces on the particle I due to other particles. So summation over j, if j is this, j is equal to 1, 2, 3 up to n. For all other particles, internal forces on acting on this Pi equal to summation Gij vector, j equal to 1 to n. Vi vector is the velocity of the particle Pi at any time t, and Gii vector equal to 0 vector because Gii vector is the internal force that Pi exerts upon itself. So this Gii vector is 0, so G11 vector 0, G22 vector 0, and so on. Now the linear momentum P vector of the system S is given by the definition P vector equal to summation I equal to 1 to n mi vi vector. So ddt of P vector, this is equal to ddt of summation mi vi vector, this is equal to mi summation mi ddt vi vector, this is equal to summation mi dvdi dvdt v is equal to 1. So fi vector plus summation j equal to 1 to n Gij vector. This is equal to summation over I equal to 1 to n fi vector plus summation over I equal to 1 to n and summation over j equal to 1 to n Gij vector. So ddtp equal to summation over fi vector plus summation over I equal to 1 to n and bracket summation over j equal to 1 to I minus 1 gij vector plus ggi vector. And this is can be written as by this note double summation over I and j gij. Actually this g11 g12 plus g13 plus g1n and plus g21 g22 g23 g2n and g31 plus g32 plus g33 plus g3n and so on gn1 gn2 gn3 plus gn. Now these principal diagonal elements, this g11 g22 g33 gn are all zero vectors. So now when I equal to 2, so g21 plus g12. So this when I equal to 2, summation over I equal to 2, so j equal to 1 to 2 is equal to g12 plus g21. This when I equal to 3, so this j equal to 1 to 3 minus 1, that is 2. This 1 2 2 1 and 3. And this when I equal to 3, this 3 minus 1, 2, so this equal to this, and I equal to 4, so j equal to 1 to 3. So this is the uh, I equal to first I equal to 1 1 3, I equal to 1 3, this when I equal to 4, so j equal to 1 2 3 and here I equal to 1, so j equal to 1 to 3, so I equal to 1 1 1 1 1 and plus this j equal to 1 to 3, I equal to uh, this, so j3 1 and j13 and this j32 j23 and so on. And now g21 and g12 are opposite, so by Newton's opposite forces, so by Newton's third law gij vector equal to minus gi vector, so cancel each other, so this summation ultimately vanishes. So this becomes this dt of p vector equal to f vector, where f vector is the total external force, sum of the external force acting on the system S. Hence the result. Next question, 7a2. Using linear momentum principle, explain the basic principle of rocket propulsion. Consider a rocket, which is a rigid body of mass capital M, which contains fuel, this removable rigid block of mass small m. The system is at rest when an internal source of energy causes the fuel back to the eject backwards with speed u relative to the rocket. Fuel block and this biological block to be rejected backwards with speed u relative to the rocket. If the system is isolated, then by the linear momentum conservation principle, its total linear momentum is conserved, which implies that capital MV plus small m bracket v minus u equal to 0. Due to this, v is the forward velocity of this. Initially, this is the rocket and body of the rocket and engine, and this is the small m is the mass of the fuel, and so after ejection, this is the small m is the mass of the fuel with the relative velocity v minus u, and this is the body of the rocket, and this velocity capital body mass is capital M with velocity forward velocity capital v. So this is the linear momentum of this part plus this part after ejection, and initially both are rest, so this is equal to 0. Initial linear momentum is 0, and after ejection this after ejection is this linear momentum is this, so this is equal to this. So hence from v equal to this m by capital M plus small m into u, and this is the basic principle of the rocket propulsion. Here we avoid this the acceleration due to gravity here. The basic principles of the rocket is this. Question 7a3. Define angular momentum of a system of particles about a point. The position of a particle p of mass m at time t is given by x equal to a theta square, y equal to a 2 a theta, z equal to 0, where theta equal to theta t theta is a function of t. Find the angular momentum of the particle P above the point A with coordinates a, 0, 0. Angular momentum of a system of particles about a point, let S be a system of particles P1, P2, Pn with masses m1, m2, mn having position vectors r1 vector, r2 vector, rn vector with velocities v1 vector, v2 vector, vn vector respectively. Then the angular momentum of the system S about the origin O is given by L L0 vector equal to summation I equal to 1 to n Ri vector cross mi vi vector. This is the angular momentum of the system S about origin, this O. And the angular momentum of S system S about any point A with position vector A vector, small a vector, is given by L A vector, that is this equal to summation over position vector, that is this Ri minus A vector, Ri minus A vector, Ri vector minus A vector cross Mi into Mi Vi vector. So Ri summation Ri cross Mi Vi minus A vector cross summation Mi Vi. So this equal to Lo vector, this is the angular momentum about O, and this minus A cross P vector. Actually, this is the linear momentum of the system. So actually, for any about angular momentum of the system at any point A, this La vector equal to Lo vector minus A vector cross P vector. A is the position vector of the point A, and P is the linear momentum of the system S. The second part of the sum, this is the let R be the position vector of a particle P. This is the path of the particle R vector. So these coordinates with a parametric form a theta square comma twice a theta comma 0. Since this is the z axis, this is the x axis, this is the y axis, and this is the position vector of the point P R vector, and this A point A with coordinates a 0, 0. So this OA is the A vector, and hence AP is the R vector minus A vector. Actually, this is the position vector of P with respect to point A at time t. So this R vector minus A vector equal to this, and I vector, J vector, K vector, K cap are respective unit vectors along the axis. A velocity vector V particle P at any time t is equal to d vector equal to dt of R vector equal to d theta R vector d theta dt. So this d theta R vector, and this R vector is this. So derive this with respect to theta, twice a theta plus twice a j cap, this I cap into d theta dt. The angular momentum of the particle P about A at any time t is given by La vector equal to R vector minus A vector cross in Vi vector. This, so this R vector minus A vector equal to this A theta square minus 1 I cap plus twice theta j cap, and in V vector is this twice A theta I cap and plus twice A theta j cap is this. So this constants, this twice m a square d theta dt, this cross product, so vectors cross product, so I cap, j cap, k cap, this component of this theta square minus 1 twice theta and 0 for k cap component, and this theta plus 1 and 0 for j cap. So after simplification we get twice m a square bracket theta square plus 1 d theta dt k cap is the angular momentum of the particle P about the point A at time t. Next question 7b1. Explain Newton's experimental law on collision. And part 2. Two smooth spheres of masses m1 and m2 impinge on one another with speed u1 and u2 at an angle alpha and alpha 2 respectively with the line of impact, and let E be the coefficient of restitution. Find the magnitude and direction of the velocities of the spheres just after the impact. Also find the impulse due to the impact and the loss of kinetic energy. And Newton's experimental law on collision: when two bodies collide with each other, their relative velocity immediately after impact along the line of impact bears a constant ratio to their relative velocities immediately before impact along the line of impact. This is the Newton's experimental law. And for the direct impact, this law states that V2 minus V1 whole divided by U1 minus U2 equal to E. This is the body A, and just before the collision, this U1 and U2, the velocity components of these colliding bodies A and B immediately just before the impact along the line of impact, and V1 and V2 are their corresponding components of velocities immediately just after the impact along the same line in the same sense. Then V2 minus V1 divided by U1 minus U2 equal to E. The constant E is called the modulus of elasticity or the coefficient of distribution, and the value of E is this 0 less than equal to E less than equal to 1. Here V2 minus V1, this numerator, is the relative velocity of B with respect to A. Actually, we call this velocity of separation. So you can remember this by this way. This is the before impact, this A body with velocity U1 in this direction, and U2 B body in this direction. So U1 minus U2, because U2 is in this direction, and this after impact, this A in this direction with velocity V1 and this velocity V2. So this rightward direction is positive and this negative direction. So this U1 minus U2 equal this, and U1 minus U2, this is the velocity of separation is this V2 minus V1, and this velocity of approach this U1 minus U2. Second part, this oblique impact, these two smooth spheres, mass m1 m2, this just with velocities u1 with the angle alpha 1, and this u2 with the angle alpha 2 with the horizon, and the center c1 c2 oblique impact obliquely. The velocity of spheres just after impact, this v1 with angle theta 1 and this v2 with angle theta 2. So the velocity components, this u1 in this direction is this angle is alpha 1, so u1 cos alpha 1, and this direction perpendicular direction u1 sine alpha 1. And similarly for velocity v1 along horizontal component is v1 cos theta 1, and this vertical downwards this the v1 sine theta 1, and similarly for v2. The velocities of sphere perpendicular to C1, C2. So velocity of sphere this perpendicular to C1, C2 remains unchanged. So V1 sine theta 1, V1 sine theta 1 is this direction, V1 sine theta 1 equal to U1 sine alpha 1. This remains perpendicular direction. Velocity of sphere remains unchanged. So this component equal to this component, and similarly for V2 is this in this direction V2 sine theta 2, and for U2 in this direction V2 U2 sine alpha 2 equals. Remember that no figure, no marks in this question. Apply Newton's experimental law. Velocity of separation divided by velocity of approach equal to E, and by the principle of conservation of linear momentum, this after collision, this after collision, this is the along the line of impact velocity component linear momentum. So this is the v1 cos theta 1 m1 in plus m2 v2 cos theta 2. Actually, along the line of impact, this linear momentum is sum of linear momentum after impact, and this is the velocity component addition, sum of the velocity components before impact is this linear momentum. Now 4 minus 3 into m2 gives this, and this simplification, algebraic simplification, we get this v1 cos theta 1 equal to this equation 5, and squaring 1 and 5, this one is this v1 sin theta 1, and this, and from 5 v1 cos theta 1. So squaring and adding, we get v1 square equal to, and we after simplification we get this. So this 6 gives the actually the magnitude of the velocity v1, this. And similarly, 4 plus equation 4 plus m1 into equation 3, and after simplification we get v2 cos theta 2 equal to equation 7, squaring 2 and 7 and adding, and 2 is v2 sin theta 2, so v2 sin theta 2, and from 7 is v2 cos theta 2, so squaring and adding we get v2 square equal to this equation 8, and this gives the velocity magnitude of the velocity v2. And dividing 1 by 5 we get tan theta 1 equal to this, and this and dividing 2 by 7 we get tan theta 2 equal to this equation 10. Now 9 and 10 give the direction of the velocities v1 and v2 after just impact. Now impulse on the either ball. Let I be the impulse of m1 on m2. Then I equal to m2 into bracket v2 cos theta 2 minus u2 cos alpha 2. v2 cos theta 2, this is the v2 cos theta 2, v2 cos theta 2 is this direction, v2 cos theta 2, horizontal direction in this after impact for this second ball, this, and this, and u2 cos alpha 2. u2 cos alpha 2 is this u2, and this angle alpha 2, this angle alpha 2. So this is the u2 cos alpha 2 in this direction just before impact along horizontal component, along the line of impact. Before impact, velocity component along the line of impact before collision, just before the impact. So this impulse, this mass m2 for second body, so this velocity after impact velocity component after along the line of impact, and this the e2 cos alpha 2 is the velocity component and just before the impact of the second ball. So I by m2 equal to this. Again, minus I is the impulse of m2 on m1. Then minus I equal to m1 v1 cos theta 1 minus u1 cos alpha 1. So this is equal to I by m1 equal to this. So adding this I by m2 plus I by m1, and after simplification we get I equal to m1 into m2 by m1 plus m2 into bracket 1 plus e bracket u1 cos alpha 1 minus u2 cos alpha 2, and this is the required impulse. Next part, loss of kinetic energy due to oblique impact. Actually, this is equal to kinetic energy before impact minus kinetic energy after impact. This before impact is half m1 u1 square plus m2 u2 square minus m1 v1 square plus m2 v2 square. And we multiply each term cos square alpha 1 plus sin square alpha 1 with this term, and this multiply this term with this term cos square alpha 2 plus sin square alpha 2 because this 1 and this 1, and with this term sin square theta 1 plus sin square theta 1, and multiply this term cos square theta 2 plus sin square theta 2 with this term. Now all our values are 1, cos square plus sin square equal to 1. So after simplification we get this term cancel, and after simplification we get actually result is given by 12. This m1 m2 whole divided by 2 m1 plus m2 1 minus square bracket u1 cos alpha 1 minus u2 cos alpha 2 whole square, and this is the required loss of kinetic energy due to oblique impact. Now note that the special cases when E equal to 1, that means the spheres are perfectly elastic. So when E equal to 1, the loss of kinetic energy equal to 0. Total kinetic energy no change, remains constant. Actually, loss of kinetic energy equal to 0. That means the kinetic energy before impact equal to the kinetic energy after impact. If E equal to 0, that is spheres are inelastic, so put here E equal to 0 here, then loss of kinetic energy equal to this, and this is the maximum loss of kinetic energy when spheres are inelastic. If E is less than 1, 0 less than E less than 1, that is the spheres are not perfectly elastic, and we get the loss of kinetic energy equal to, and this quantity is positive quantity. And in 2016, this question, when M2 equal to twice M1, then loss of kinetic energy equal to, put this M2 equal to twice M1, M2 equal to twice M1, and then simplification, we get loss of kinetic energy equal to M1 by 3 bracket 1 minus E square bracket E1 cos alpha 1 minus E2 cos alpha 2 whole square, M1 not equal to 0. And this ends the question paper 2021 CC-10 mechanics. Thank you for watching this.